Okay, so what we're gonna go over here is just kind of a demonstration of the central limit theorem, right? So just kind of to rephrase what the central limit theorem states is that if you have some distribution, right, your data is coming from some distribution, and you don't know what the distribution looks like, right? But you know the mean and the standard deviation, right? So what you can do is you can sample from this distribution, right? And with replacement, so you can you sample it and then you introduce those back into the population and you sample again and again, right? Now, the mean of those samples, right? Now that is normally distributed, right? So what we have here, right? If you see here, I've chosen this particular demonstration to have a skewed distribution just to see that the sampling of it will lend us a normal distribution. Right now, skewed, this one has a choice so you can uniform, right, where equally likely all the outcomes here skewed, right, in this case skewed to the right, where we see the outliers are on the right tail here. Okay, so what we're going to do first is we're going to have n equal to 10, right? All right, let's make it small, let's say 5. Okay, so what that means is, if you see, I'll take 5 samples, and then I'll take the mean of these, right? So the mean here being this value here, right? And what the central limit theorem states is that you keep doing this over and over again, right? You take 5 samples, you take the mean of that, right? And that's what you see here in the third one from the top, right? Each one of these represents the mean. All right, and let's do this. Let's speed up the process here. Let's do 10,000 of them, right? So this is a rather large number. Now what you see here is what we're seeing again is the mean, right? So these are in blue. All of these represents the samples that we take, and we take the mean of those samples of size 5. Right, now if you notice here, right, looking at the different parameters and statistics here, right, after doing it 10 times here, the mean of our population is 8.08, and the mean here of our sampling distribution is 8.09. Right, and you see how the distribution here fits a curve, right? Now, one thing to notice is, right, the mean of the sampling distribution will be the same as the mean of our population distribution. Okay, so one thing here is that it doesn't fit perfectly. Again, as always, well, there are always going to be some kind of variation, right? That's just the nature of what happens when we start sampling, right? We can't get away from variation. Now, let's take a look to see. So this was a sample, not a very large sample, right? And again, notice here in the theorem, it states that the sample is large enough, right? And usually what that means is about 30. Now this doesn't allow me to go to 30, but let's look at this 25, right, and see if that improves our sample in any way. Right, so again here, what's happening, right, this one's going to take a while, right? So it's sampling from our population. Okay, it takes 25 of these, right? Then it takes the mean of those, right? So that's what we have here. So let's see again. Samples from the population. Takes, in this case, 25. And then once it finishes taking those 25, it takes the mean. All right, so let's speed up the process here. Let's do 5 at a time here. Okay. Okay, so each one of these is doing 5 of these. Sample 25 times, take the mean. It's doing that 5 times. Now let's go even faster than that. Let's do 10,000. Okay. All right, now what you'll notice here, again, this looks a little not as wide as the previous one that we did, right? And what we can see here, right, here the mean is 8.08, and this is almost like, right, exactly the same here, at least to 2 decimal places, right, 8.08. All right, and notice that the higher the sample is, right, the more narrow it becomes, because if you notice the equation for the sampling distribution, right, you're always dividing by the square root of n. So what that means is as n gets larger and larger, your standard deviation gets smaller and smaller, right? In other words, this peak, right, will just get higher and higher, all right? So it won't be as spread out. Right, so that's the idea here of what the central limit theorem is, right? Where you might have some initial population or some population that we're interested in kind of analyzing, but I don't know what the distribution of it is. Well, if I sample from it, and if this sample is large enough and take the mean of these samples, that I'm guaranteed to have a normal distribution, right? Which, as we've seen from the previous module, is rather straightforward to work with. Okay, thank you.